Hello again. Now, the situation you're going to examine today, we've all experienced this, whether it's when you get that hot cup of coffee from Starbucks that you all like, or you take a batch of freshly baked cookies out of the oven, or anything like that. You want to cool it off. We all have experienced this act of hot objects cooling when you place them in cooler air. So let's take a look at this law here. Um, and again, I think you've all experienced this. What the theory behind what's happening is the rate of change in the temperature of an object, presumably a hot object in a cooler environment. The rate of change of that object's temperature is proportional to the difference between the object's temperature and the temperature of the surroundings. So again, you've all experienced this. What's the best way to cool off something really, really hot is to put it in the coolest environment you can find. So, whether it's, you take something really hot out of the oven and if you want to cool it off really fast, well, you take it outside on a cold day or something, or put it in your freezer because that's the coldest environment you can put it in and it cools the quickest. Okay, now what that also says is then as it cools, the rate at which it cools should slow down, meaning the closer the object's temperature becomes like the air temperature around it, it should decrease the rate at which it's cooling. So in other words, when it is very, very warm, when the object is very hot compared to the surroundings, it'll lose a lot more degrees per minute or per second than it will as it cools and gets closer in temperature to the air temperature. And the same would happen if you submersed it in water or whatever. So the surrounding medium doesn't have to be air. It could be putting it in water or just anything that's colder than what the temperature is. Okay, so this is going to represent in a way, uh, a model for a type of exponential decay. So imagine that the graph would look like this. Okay, so let's let y be the temperature of the object, the hot object's temperature, and then this will be time. So what's going to happen is it'll start off at some really high temperature, and it will start to go down in temperature, not in a straight line, but in a exponentially decaying fashion. And it's because the steepness of this curve will decrease the closer the temperature becomes to the air temperature. So somewhere down here is the temperature of the air. I'm just going to put a capital T and subscript that with an A. So that's like the air temperature. Somewhere lower than the original hot temperature is the air temperature. And so as the object cools, we know that it can't go lower than the air temperature, right? So there's going to be this horizontal asymptote that is the same as the temperature of the air, or if you've doused it in water, if you've submersed it in water, whatever the water temperature is, whatever. But so your graph's going to go like this. And so this law says the further away from the air temperature the object temperature is, the steeper the graph. It's going to cool off quicker, and then the closer it gets to being the air temperature, the slower it will cool off, right? So the equation we're actually going to write will imply that the object's temperature will never exactly be the same as the air temperature because of the asymptote here. Okay, but anyway, so the goal for today is to change this statement into a differential equation, solve the differential equation using some calculus, and then we'll solve some actual problems using the model. Okay, so let's actually write the model first as a derivative or differential equation, starting with the phrase, the rate of change in temperature of an object. Now, actually, what we should do first is define our variables. And I've already kind of started to do that. Y will be the object's temperature. It's the dependent variable. Object's temperature. Now the scale, the units might be degrees Celsius or degrees Fahrenheit or kelvins, but whatever have you, but that'll be specified in the problem we're given. the dependent variable, the independent variable is time t. Okay, and again, the units of that will be mentioned in the problem. And then capital T, this will be the air temperature, and it will be remaining constant. So this will be the constant air temperature. And then finally, there's going to be a constant of proportionality because of the fact that we have direct proportionality here. So there will be another proportion constant. We'll specify that right now too. Okay, so let's translate our sentence. The rate of change of the temperature of the object, so the rate of change of y with respect to time, so dy dt is directly proportional to, so is equal to k times. Now this is where it will start to be different than last time. In the exponential growth model, the rate of change of y was proportional to y, and that was all there was. Today, it's proportional to the difference between the object's temperature and the temperature of the surroundings. And so the difference is to subtract. The object's temperature is y, and the air temperature is this capital T. Okay, so here is our model. Now this is often referred to as Newton's law of cooling, referring to Isaac Newton. And it'll appear in a lot of chemistry and physics books, probably not in this form. They probably just go ahead and give you the equation for y as a function of time, which is what we're going to use calculus to do next. So let's take our derivative one more time. Dy dt, d little t, is proportional to the difference of the temperature of the object and the air temperature. Now keep in mind, there are already two constants in this equation, k and the capital T. So when we want to separate the variables, we want to separate the y from the little t, the time. So we're going to bring dt, change in time, over to the right. We're multiplying by dt. Now to get the y over with the dy, we're going to have to divide by this entire quantity, the difference of the two temperatures. So we're going to divide by y minus capital T. And we'll keep the constants of proportion on the right. That'll leave two relatively easy integrals to solve. Okay, so the easiest integral is the one on the right. K is a constant, and we're integrating dt, so it'll be kt. And now we have to introduce a third constant, the constant of integration, plus c. Now for the integral on the left, it's pretty close to being dy over y, which is a natural log. It's so close, we're going to make a u substitution. U equals y minus capital T. And that way du is dy. Remember, the capital T is a constant. And so this integral will be solved by rewriting it in the form du over u, which is natural log of u. And u was y minus capital T. So this is going to be the natural log of the difference of y and the air temperature. And so there we have it. Now the goal is to solve and get y explicitly as a function of the time little t. So since it's involved in a log here, we'll just take e to the power of each side. You've seen this done hopefully quite a bit now. And so the e to the power of and then the log, they cancel. Okay, so the left side now is just y minus the air temperature. Over here, we've seen this lots of times too, hopefully now. This entire quantity, kt plus c, is the exponent of e. So your thinking here, remember, is this is like doing e to the kt times e to the c, and this entire quantity is another constant. We're going to call it capital A again. Okay, so we're going to refer to that as A, and so I'm going to write the right side as A times e to the kt. And finally, we would bring the temperature of the air back over to the other side to get y by itself. And so I'm going to write it like this: air temperature plus a e to the kt. This is what would mostly likely appear in your science books. Here's the law, Newton's law of cooling, as an explicit function. The object's temperature is now explicitly a function of the time little t, and in terms of these other constants, the air temperature, the proportion constant from the differential equation, and then this other constant a. Now let's examine it a little bit closer too, because it plays a neat role here. If you actually go back up one step and look at the equation we had right before the end, and suppose we were going to examine this at the very beginning of the experiment, like let's say the time was 0, right? So if the time were 0, the left side would still be the difference. Now this would be now y of 0, right? The initial temperature of the object minus the air temperature. And here you'd have a times e to the 0, and e to the 0 is 1. So what this tells you is that the constant a in our function is really the initial temperature difference, right? So it's the starting temperature of the object subtracted by the air temperature. So capital A is the initial temperature difference. And there's usually enough information given to you in problems like that involve this that you could determine that right at the beginning, right away, and just know that's going to be your A. It's a common mistake, though, to think of this like it was an exponential growth, where in the exponential growth model, that same constant was just the starting population or the starting quantity y. This time it's not. It's the starting temperature difference. Okay. It's the difference of the two initial temperatures, the air temperature and the object's temperature. Well, we'll be back in video number 2 where we'll solve a couple of problems that involve this law.